Welcome back. Today's video is going to be about free fall, and I'll do another catch-up problem on top of that. So these problems are going to be starting on page 14. You might have done a catch-up problem already on page 13. I believe questions 71 and 72 are catch-up problems. And if not, you can try them later. That's not a big deal. So hopefully it should be a shorter video, but there should be about 24 questions. Questions 1 to 17 are fairly straightforward. They're mostly just free fall problems. Question 18 to 24 are a little bit more challenging. So you'll want to, when you attempt those problems, you'll probably want to use a full page in order to do them all. So let's get started here. There's a bit of an echo in this room. I'm using my classroom, so I'm using a little webcam here with a mic on it. So there'll be a bit of a echo feedback, and for that I apologize if you're a bit of an audiophile. So free fall is an object that is going to be accelerating vertically by gravity and only gravity. Very often there's no initial velocity, so a lot of these problems you're going to hear an object was dropped or released from rest or just released, or point being is there's no acceleration other than gravity. And of course gravity has a value, g is equal to 9.81. So this is your acceleration of gravity is equal to 9.81 meters per second square. That's the global average. Now, of course, this is a vector. It is going downward. So sometimes you'll want to make down the positive value, and so therefore you consider it a positive 9.81 meters per second square. And sometimes you'll want to use up as a positive value, and then you have negative 9.81 meters per second square. So this is an acceleration. Technically, it's a gravitational field, but we'll get to that in another lesson. So for most of these problems, in fact, all these problems we're going to do in this unit, this is the key thing here. We're going to assume that air drag does not play a significant factor in these questions. Air drag is real, obviously, but usually you have to start going fairly quickly before air drag becomes an actual factor that you have to consider. So by and large, if you're just talking about slow moving objects, and of course by slow, there's air quotes around slow, we can more or less just assume there's no air drag. So we'll dive right into it. So we're going to end up using some of the kinematic equations, but for the most part in these kinematic equations, anytime you see where you have the acceleration, you basically just have to consider that as the acceleration of gravity at this point. So I believe this is question number 3 in your little work booklet on page 14. It says George starts his stopwatch just as he dropped it from the top of a building. When he recovers on the pavement below, it is smashed and reads 5.1 seconds. Obviously not a smartwatch, because a smartwatch screen probably wouldn't display anything at this point. So we're going old school. How high is the building, and what speed did the watch hit the pavement with? So this is a two-part problem. The first part is to identify what is given to you. So try to think up all of the givens. So I see one number sitting right there. So that tells me I was given time. So time is 5.10 seconds. I also know that it was dropped on Earth. I know it doesn't explicitly say Earth, but to our knowledge, Earth is the only place humans exist. So therefore, you just have to assume that our acceleration is that of gravity. And so therefore, your acceleration of gravity is, once again, 9.81 meters per second square. And I'm going to make down the positive direction. And so therefore, I have a positive 9.81 meters per second square. All right. It also tells me that he just drops it. And so if an object is dropped, its initial velocity is going to be 0. It's released from rest. And so from that point, we have to find out how high was the building. So we are looking for this overall height, which is your vertical displacement. And so therefore, if we find the distance it goes, the displacement it travels downwards, that'll tell me how tall the building is. So we need to find an equation that uses all of these 4 variables. So time, acceleration, initial velocity, and displacement. So that would be kinematic equation number 3. So kinematic equation number 3 says that your displacement is equal to your initial velocity times your time plus 1/2 your acceleration. And since I'm using the acceleration of gravity, I'm just going to replace the a with a g and times my time squared. Now, the other thing I like to do when something is dropped, I just remove that first little bit there, because 0 times your initial time is still going to be 0. And so often this gets rewritten like this. This is typically seen as the free fall equation, assuming that an object starts from rest. And so that simplifies equation 3 a little bit. And so after that, you would just plug in your terms. You have 1/2 your acceleration of gravity, so 9.81 meters per second square, multiplied by your time of 5.10 seconds. And of course, we will square that. Please don't forget that you're going to square the number and the unit. And so therefore, it would look like this. So half my value of gravity should be 4.905 meters per second square. And when you multiply 5.1 squared, you should get something a little around 26, if I'm not mistaken. Let me just plug that into the calculator real quick. Well, I don't think on the fly well when I'm doing these videos. Yeah, about 26.01. So I'm only doing this step here just to kind of make sure you recognize that, as I said in this green pen before, you have to make sure you square both the number and the unit, because we want this per second squared canceled with that second squared whenever you're doing this math, because you want your units to work out in the end. So do that math. Almost 5 times roughly 26 will probably give you a number around 125. If I do some quick math, you'll get around 127.6 meters, which is what your calculator would say. If I round this to follow the rules of significant figures, I would have to say that it is a 3 significant figure value. And therefore I have 128 meters is the approximate height of that building. And that is probably what your answer key will say at the back of your book. So that is part A. Part B, with what speed did the watch hit the pavement? So we're looking for the final speed. You could argue I should look for the final velocity, but we'll look for the final speed. So when something hits the ground, what just happened there? When something hits the ground, sorry about that. Most people think, oh, it hit the ground, so it must be at rest. Well, typically when you hit the ground with a final speed, right? You are still moving. It's not until the ground acts on the object that the speed will change. So you have to keep that in mind when you're doing a problem like this, right? It will always hit the ground with a final velocity that is not 0, right? It's not until the ground acts on it that it'll actually cause it to slow down, but we'll get to that later. So in part B, we are going to use basically the same givens provided. We're going to reuse these. I could use the displacement I just found, but I tend to not use values that I just calculated if I don't have to. So I'm going to use the same 3 givens as before. I got my initial time, I've got my acceleration of gravity, and I've got my initial velocity. So therefore, I'm going to probably use equation number 3. My final velocity, I know it asks for speed, but I'm going to find velocity anyways, is equal to my initial velocity plus my acceleration. In this case, I'm going to replace my A once again with the letter G because it's accelerating by gravity, times the time. And updating this, considering my initial velocity is 0, I can rewrite this equation to account for a free fall situation where there is no initial velocity, which is often the case in many of these free fall problems. The initial velocity doesn't need to be 0 to be considered free fall, but very often it is. And so therefore, we're going to use this equation right here. It's a nice straightforward equation. To find the final speed of any object, if it's released from rest, you just need to multiply the time it's falling by your acceleration of gravity. And so in this context, I'll just take my 9.81 meters per second square. I'm going to multiply it by 5.10 seconds. I've got 3 sig figs all the way through, and recognize that this square down below here is going to get canceled by that second there. And if I just do some quick mental math, I'd say it's probably around 50, but I'll use a calculator to double check. It is around 50. So 50.03 is what your calculator is going to say. But you guys just need to write it down with 3 significant figures. I solve for it to be positive, so that means the final velocity is going downwards at 50.0, and my units that remain are meters per second. Right, and so that's just an example of a free fall problem. Some free fall problems you might have to solve for other things like your initial velocity or your time that it was falling for. So that's something you can explore when you try other problems. Catch-up problems can be a little more challenging because you often have 2 bodies that are moving simultaneously. And so often that means you're looking for some kind of overall displacement, whether or not it's the displacement of 2 bodies that are trying to catch up to each other or one body trying to escape the other body. So there's a couple of different ways we can go about this. I'm not going to obviously read what's on the screen to you. You can read that on yourself. Typically, for a lot of problems, I find dumping vectors tend to make it a little bit easier and just figure out what their overall distances are. And I'll show you what that looks like in this next problem. So I'm going to use question number 19 as my example problem. And so number 19 says a block of wood is thrown straight down at an initial velocity of 9.80 meters per second from the top of a cliff that is 58.8 meters high. At the same instant, an arrow is shot straight upwards at the block of wood with an initial velocity of 19.6 meters per second. How long will it take for the block of wood and the arrow to meet? Now, a problem like this, I typically recommend that you draw out the scenario. Sometimes these problems are a bit easier to dissect if you can actually visualize it. And sometimes thinking in your head is hard. I should know. I have to do that every once in a while. You wouldn't know that from being in my class. So I'm going to draw a cliff. So this cliff is 58.8 meters high. So that is the overall total distance of my cliff. So 58.8, that's terrible penmanship, very sorry. So I'll write it vertical. My total distance is 58.8 meters in height. Okay, there's the ground. Obviously not drawn to scale. I have a block of wood. There's my block of wood. That starts off with an initial velocity of 9.8 meters per second going down. And so my block of wood is going to go down. So for that reason, it has a speed. I'm going to call this VIW for the wood of 9.80 meters per second, but it is going down. So velocity wise, I want to decide whether it's positive or negative. Speed wise, I don't care about the actual direction. So I am going to use speed in this and distances and just dump the vectors, and you'll see why in a moment. But first, still going to set this up. What else do I need to know? So that block of wood is going down. And while it's going down, acceleration, on the other hand, is that of gravity. So the acceleration of the wood, there's no way you can get around an acceleration not being a vector. But in this case, we can kind of consider, well, what is G doing to the wood? So the acceleration of gravity of the wood is actually going to be positive 9.81 meters per second squared. The reason why I just call it positive G is because that's what it's doing. It's the positive value of 9.81 because it's going to cause that block of wood to speed up as it's falling. And so I would much rather use that as just a single value of G. Right? So anything that's dropped should start to speed up. Now the arrow, on the other hand, the arrow is shot straight up at the block of wood. And so to draw an arrow, I'm not very much of an artist. There's my arrow. I'll give it a bit of a quill. There you go. Again, not a very good artist. Now the initial velocity of the arrow is going upwards. So whether it's positive or negative is up to you, but I'm not going to draw it as a vector. I'm just going to use the speed, 19.6 meters per second. but I need to consider what its acceleration of gravity is going to be. So its overall acceleration of the arrow, so acceleration of the arrow is going upwards, which means it's going to slow down. Anything you throw up in the air is going to start slowing down at the rate 9.81 meters per second square. So since it's going to slow down, I'm going to call it negative 9.81 meters per second square, which I'll just leave it as negative g. And you'll see why I'm not using numbers in a moment or two. So if you can get away without using numbers, great. I tend to like to do math without numbers whenever possible. So the next part of this question asks, how long will it take for the block of wood and the arrow to meet? So what it's actually asking for is, what is the time in which they meet? So of my givens, I have my initial speed of my wood, I have my acceleration of gravity of the wood, I have my initial speed of the arrow, and I have my acceleration of gravity of the arrow. I do have a distance. However, the time in which they meet, I don't know how far down they're going to travel. I don't know whether or not this block of wood is going to hit right there with the arrow traveling up there. I have no idea where these guys are going to meet. I do not know what the distance traveled of the wood is, and I have no idea what the distance traveled of the arrow is. Now, again, I'm going to use distance, a scalar value, so I don't really have to worry about whether or not they're positive or negative. But since I don't know what this is, and I don't know what this is, that kind of makes this problem a little bit more challenging. I do know that if I look at what I have here, if I actually find this distance and add it to this distance, I will get my total distance. So therefore, where this question becomes a little more tricky is I can create a scenario where the total distance is going to be equal to where the distance traveled by the arrow plus the distance traveled by the wood. In other words, where they meet up should be the overall total height of the actual cliff. Now, because I don't know what the distance the wood travels and the distance the arrow travels, I would have to find those out separately. So I'm going to scroll down my page so I have some room to write. I recognize that the distance traveled is 58.8 meters, so I've got that number. But I need to recognize that for the givens that I have initial speed, I have acceleration, I'm kind of looking for a distance, and in the end, I want a time. So an equation that satisfies this, that has initial speed, acceleration, distance, and time would be equation number 3. So I'm going to input in equation number 3 where I see the distance of the arrow. So therefore I have the initial speed of the arrow times the overall time in which they meet, plus 1/2. Now my acceleration of the arrow is going to be always a vector, so I can't get out of that. So leave it as a vector times my time squared. So this is for the arrow. I'll just write down below my horrible chicken scratch. That is the distance traveled by the arrow. I need to add to that the distance traveled by the block of wood. So the block of wood has the same parameters. You know that you're in the end looking for the distance the wood travels. You have your initial speed of the wood, you've got your acceleration of the wood, and you're solving for time. And so therefore, I would use the exact same equation. I would just use the variable specific to the wood. So I've got the initial speed of the wood. I've got to multiply it by the time, since they were dropped, they were released at the exact same amount of time. Time is going to be the same in both equations. Plus the acceleration of the wood, that is always a vector, times the time squared. So this here is for the wood. So at this point, I'll want to plug in all the numbers that I know. By doing a catch-up problem this way, I have effectively removed the need to actually solve for either of those two distances. All right, you'll see there's no distance here, there's no distance here. It's the equation for that distance, but you don't actually have to solve for it. So it's one way of getting rid of an unknown. And you're going to find that lots in a physics class, that sometimes you have too many unknowns and you have to create an equation by substituting multiple equations together, and it will often get rid of an unknown term. So at this point, we're going to just plug in some terms. So this we know is 58.8 meters. My initial speed of the arrow is going to be 19.6 meters per second multiplied by the time of delta t. Plus, I have the arrow 1/2. I'm not going to use the number. I know 9.81 represents meters per second square is technically g, but since the arrow is slowing down, I'm just going to call this negative g. And of course, I have that unknown time. For my block of wood, same idea. Again, I'm just using the speed. So the speed of the wood, if you remember, is 9.80 meters per second multiplied by the unknown time. And I'm going to add to that 1/2. Now with the wood, I'll scroll up for this because you can't see it anymore. The wood, if you remember, should be speeding up as it's falling down. So I'm going to use positive 9.81 meters per second squared, but I'm not going to write the number out. I'm just going to leave it as a symbol because that keeps life a lot easier. So that is what I know. I have a lot of symbols still yet to be written out as numbers, but I do want to point out that ideally, see that 6 looks bad. Ideally, when you're trying to solve for these things, you want to group like terms, right? I cannot technically add these two together because obviously I've got a quadratic. So I want to group like terms. So I have one quadratic here. I've got one squared term there. And if you'll notice, one is 1/2 negative g. The other one is 1/2 positive g. So if you're decent at math, you probably recognize that they will cancel each other out. The rate at which one object is slowing down because of gravity should be the exact same as the rate at which one object is going to speed up because of gravity. And so because of this, they will cancel out. So it actually gets rid of a lot of the math. And so what's left is you just have this term and that term. Now they have the same unknown variable, delta t, so you can just add them together at this point. A little bit messy, I know, but hopefully you followed along. And so you end up with 58.8 meters. Add the 9.8 to the 19.6, and you should get 29.4 meters per second multiplied by your actual time. And so at this point, just divide by your 29.4 meters per second. That'll cancel out. A meter will cancel out that meter, and I end up with a per second in my denominator. That's all that's left for units. So if I have a per second left over, that just becomes a second. And so if you do that quick little math, you will probably get something to the effect of 2.00 to 3 significant figures is equal to your actual time. And that's how you would kind of do that specific problem. There are other types of problems. I don't believe any two of these catch-up problems are the same. But a lot of the times you'll end up taking this similar method for a handful of them. All right, so don't feel like this is the only way to do a catch-up problem. This is just one way of many. We got lucky with this problem because it said that they were released at the same time, and so therefore we didn't have to do anything fancy with our time. Sometimes, there we go, same instant. Sometimes it'll say something like, the questions will say something like, one object was released and then 1 second later the next object was released or thrown, for instance. And then you have to play around with time a little bit more. I'll show you an example of that in person when you're in class. But this is for just to get you started for now. So if you have any questions, do send me an email. I'll try to get back to you as soon as I can. But other than that, good luck with this. Yeah, I'll stop there somehow.